So here are your notes on solutions. This video is going to go over the properties of solutions, solubility, and the factors that affect solubility. So let's begin. These things are called homogeneous mixtures. Might be a term that you remember from the beginning of the year. If it were me, I would go back to your matter unit, and I believe we have a concept map. So find that and kind of look at it. Homogeneous mixtures are by definition aqueous because something is mixed with water. Consisting of a solution, we have a solute, which is usually something solid. In the case of liquids being dissolved together, it's usually the smaller amount. Usually it's mixed in some type of liquid called the solvent. For the most part it's water, and that's usually considered the larger amount. So some examples, KCl is dissolved in water. KCl would be the smaller amount, so this would be your solute. H2O would be our liquid, and we would be left with an aqueous solution. So again, look back, find your concept map, and also look at the PowerPoint to review the types of mixtures. So let's talk about solubility. Solubility is the ability to dissolve. That is a physical property, and that when you dissolve two things, their properties do not change. Two terms you might be looking at, soluble and insoluble, which you'll find on table F coming up. Soluble means it does dissolve well. So some examples of that would be salt and water. And this term insoluble, sorry about that, means it's a substance that usually doesn't dissolve. So if it doesn't dissolve, it's basically going to stay as a solid, and you can usually see it at the bottom of your container. So some examples of this would be, say, rubber is insoluble in water. So we're going to be using table F. Table F takes those two terms and tells you whether or not something is going to be soluble or insoluble in water. So just keep in mind, we have three types of compounds. We have ionic compounds, covalent compounds, and metallic compounds. So if you think about it, two metals you can't mix together in a liquid and it will dissolve. So that's probably not a solution. Covalent compounds are pretty tightly bonded. So more likely than not, they are going to be insoluble. So when we are talking about compounds being soluble or insoluble, most of the time, ionic compounds are soluble. But like anything, there's always exceptions, and that's what table F is all for. So, and also just to kind of add in, since you guys know about the different types of reactions, the addition reactions, substitutions, these are considered double replacement reactions. So that just means two aqueous, like we said, ionic compounds are mixed together. Think of when we were in class and we did the switching of the partners, marriage swap. They usually form a solid in some cases, and this is called a precipitate. Nice way of saying solid. And table F is going to lead you to figure out if it's soluble or insoluble. All right, so what affects solubility? You might know this because you've probably tried to dissolve something in water before. So you've probably tried to put sugar in water, salt in water, Kool-Aid in water, iced tea mix in water, coffee in water. So keep in mind, we know that if the temperature is hot, like boiling water, that works well to have coffee and tea seep through. So as you increase the temperature of the water, more likely than not, the solid is going to become more soluble. So as the temperature of water increases, solubility is going to increase. So some examples, the other thing that affects solubility is pressure. So as pressure on a solution increases, solubility actually stays the same. But think about that. What are some of the things that we put under pressure? Do we put solids under pressure? No. Because in the example of solids, those are the examples that stays the same. But if you think of soda, we know that if you increase the pressure on a solution, it's going to increase the solubility. So in the example of soda, we have CO2. It's dissolved in the soda can until you pop that top, and the carbon dioxide is going to come out. So let's go back up here and look at the examples of solid and gas for temperature. Okay. Do solids dissolve within solids? Most of the time not. So in the example of a solid, it stays the same. But when we're talking about a gas, as the temperature increases, believe it or not, the solubility decreases for gases. So what does that mean? If we were to look at, say, global climate change, we know that the temperature in our environment's going up, and ultimately warmer temperatures assist in different weather patterns, but also it releases a lot of the carbon in the form of carbon dioxide in an ocean. So as the temperature goes up, we don't have the ability to hold those gases, so the solubility is going to decrease. Okay. Now, in the example of a liquid and a solid, that is going to increase as the temperature increases. So those two things, pretty much you can see. You can keep the example of coffee and soda on your mind. And the last part is polarity. So think back to the other units where we said like dissolve like. So in that case, nonpolar molecules will dissolve other non-polar molecules. So if you remember when we did the demonstration with the alkenes and compared that to the amount of water next to it, we saw that the alkene was evaporating a lot quicker, higher vapor pressures. So in the example of, you can use that as an example in your head, or you can also consider, alcohol and iodine. So believe it or not, if you've ever been to the doctor and instead of getting an alcohol swab, you might get an iodine swab. Now iodine is usually a solid, can be a liquid, and it's pretty cool in that it can actually become a gas from a solid state. Now, iodine is good because it's a disinfectant. That can be mixed only in alcohol. It cannot be mixed with water. Polar molecules like water dissolve with polar molecules like water. And we can also keep in mind that most of the time it can be with ionic compounds. So one question that usually shows up on reagents is, how do these orient themselves to the negative ion? So in the case of a water molecule, okay, we know that kind of looks a little bit like Mickey Mouse. Okay, the slightly negative part is usually the oxygen, and the slightly positive part is the hydrogens. So if I were to draw this, the hydrogens would be aimed towards the chlorine atom.